and Alan has informed me that there's a better talk across the hall, so that every one of you is here with mixed feelings. So I'm flattered. It's a 60th birthday talk. I won't attempt to prove anything, and indeed I don't have any theorems to prove, and indeed there are at least 10 people in the room who know far more about this subject than I do. So I make no claims. I probably know as much about this subject as the average person in the room. So there's this chap Edelman, and he was a young man, and he was my student back in the 80s, a total star undergraduate at Yale. He came to MIT, he wasn't sure what to work on, but eventually he decided to be my student. That's the best thing that ever happened to my career. And in the summer of 87, he came to Oxford. I wasn't there yet, I was just visiting. He came to Oxford, and we had a nice summer together. I wanted him to explain the stability of Gaussian elimination with partial pivoting, which is still not explained. And to do that, we were looking at random matrices, and that, of course, launched part of Alan's career. This paper was great. It really hit the headlines. This is in a day when the field of random matrices, of course it existed, but nothing like what it is today. Alan wrote this amazing paper. It's actually the same title as his thesis, and actually, I think I brought with me actually, I forgot this. I'm not doing this for drama. I'm doing it because I forgot it's in here. Yeah, okay, so there's the thesis, which we made into a tech report. You probably have some copies. But
I have some copies.
Okay, give it back to me afterwards. Anyway, beautiful, beautiful work. Also beautifully displayed. That's not so beautifully displayed there, but you get the idea.
That was Mathematica in 1989, which was its first year.
Yes, so Alan was like the first guy to do both MATLAB and Mathematica. I mean, one of the first to really use these tools. So there he is, and I have to thank Alan, in fact, for sending me these pictures. So he's a kid, he's 23 years old or 4 years old. There's a picture with Alan and half of me. And of course, people dress up sometimes at Oxford. You don't wear ties so much, I suspect, now. Alan also sent me this. I guess he turned 24 when he was in Oxford, so that says, happy 24th, and thanks for coming to the far side of the Atlantic with me. And there's another picture from 10 years later on the beaches. It's on Ipanema Beach, I think. So happy, happy memories. You can see we're already a third of the way through the talk, so you get a sense of the depth of my presentation. So my subject is to connect random matrices with smooth random functions, as I call them. So I'm interested in this notion of a smooth random function, which is defined by a finite Fourier series with random coefficients. And I'm not going to go into the details of that, but it was published in Science Review, and this is something I've been using ever since. My life is lived in ChebFun, and ChebFun has as one of its basic operations constructing these smooth random functions. So there's a picture of a smooth random function on the sphere, always defined by a Fourier series with random coefficients. There are many ways you could choose to do this, but we do it simply with every coefficient from the same Gaussian distribution, independent Gaussian coefficients. And the only issue is, how big should your finite Fourier series be? How many terms? And what we do is we have a wavelength parameter lambda, and the number of terms in the random Fourier series is inversely proportional to lambda. So as your wavelength goes to 0, the series goes to infinitely many terms. So I think that's a very natural computational and mathematical thing to play with. Physicists do it all the time. I think mathematicians are a little less interested in this point of view, but of course it's a standard way of thinking which basically goes back to Norbert Wiener in the 20s. So there's a picture of a one-dimensional smooth random function, and as I say in ChebFun, there are commands for this in 1D and 2D, on a sphere and on a disk. For some reason, we never implemented the 3D version, but we could. Okay, so those are the idea of smooth random functions. Now, let me tell you the terminology we use. So that's a matrix. It's a discrete object. That's a quasi-matrix, which means continuous in one direction and discrete in the other. And that word, I think many of you know this word. It was made famous by Chebfun, I guess, but the word comes from Pete Stewart, and he wrote a paper in the 90s mentioning this word quasi-matrix. And then a weirder word that is certainly not so well known is C-matrix. So Alex, hi Alex, I haven't said hi. So Alex and I wrote a remarkable paper. I was on sabbatical in Geneva at the time, and we were interchanging emails all the time and working on this problem of continuous analogs of matrix factorizations like LU and so on. In fact, Gil Strang had told me what an LU factorization meant for the continuous case years earlier, and we were working out that and other ideas. And we found that although that object is just a function of two variables, when you want to talk about the matrix kinds of operations on it, it helps to have a word for that. So we call it a C-matrix. And this is, it's a very pretty paper, I think, in Proceedings of the Royal Society. So I really like that paper. Now you may ask, why the Proceedings of the Royal Society? So I will now explain that to you. Alex is smiling. We sent it to Siam Review. So now I'm going to show you what the referee said. It's got an outdated flavor. It's unacceptably sloppy. It's inappropriate at best. It's got sloppy exposition. Frankly, I don't see the point of the paper. It's misleading at best and dangerous at worst. I did not get any insight. A severe misrepresentation of the field. The scholarship is not up to the standards of Siam Review. The bibliography and setting of the context are woefully inadequate. The authors cannot be serious. And I'd like to see this for 3D problems, multi-scale, multi-physics with uncertainty. Let's start with the simulation of a wing attached to an Airbus in turbulence. So we submitted it to another journal. Okay, back to the topic. So there's a picture of a random matrix, and what I've done is I've taken a matrix, and it's just RandN in MATLAB. It's independent, normally distributed entries, and white for positive and black for negatives. We call that a zebra plot, or in England, a zebra plot. Now, there's a random C-matrix, so it's the same kind of plot of a two-dimensional function, a smooth random function defined by a bivariate Fourier series, finite Fourier series with random coefficients. Now, that's the way I like to plot things because it's so crisp and simple, but of course, we're talking there about a function, which of course is a function, so you could, if you prefer, plot it in other ways. The right scaling, and I won't go into this, is to take our wavelength parameter to be 2 divided by n if you want to make the analogy between a random matrix and a random C-matrix. So the theme of this talk is, what can we say about singular values and condition numbers of those things? And you will see that it's very much like the random matrix case with just 1 or 2 differences. And I don't have theorems, just experiments. An observation about random matrices. So there again is a picture of a random matrix. Now, of course, we think of a matrix as occupying an m by n rectangle, or I'm going to say gamma n times n, where gamma is a constant bigger than or equal to 1. So a random matrix we think of as on that big object, but to compare it with a random function, it's convenient to rescale to an object of size O of 1. So the rescaling is to think of this picture as living on a rectangle of 1 by gamma. And it turns out that the right way to do that rescaling, random matrix conventionally would have variance 1 over n, standard deviation 1 over the square root of n. And the reason is that makes interesting things scale cleanly as n goes to infinity. So for example, the norm of a random matrix converges to something if you scale the entries like that. Well, when you change your rectangle to be 1 by gamma, it turns out the right thing to do is multiply the standard deviation by n. In other words, multiply the variance by n squared. So again, we have an object that will converge, it'll have norms of size 1 as n goes to infinity, or lambda goes to 0 in our case. And there is an analogous C matrix, a smooth random C matrix, 1 by gamma, and it's defined by a finite bivariate Fourier series of length 1 over lambda in each direction. So there's a not deep observation, but a convenient way to think of things. A matrix is a special case of a function that is piecewise constant on squares, okay? And you know, I've spent a lot of years working with ChebFun, which is all about continuous analogs of things. And the starting point of ChebFun was you take a command in MATLAB and you ask, what's the continuous analog of that? What should you do with functions analogous to what you do with vectors? Or what should you do with operators analogous to what you do with matrices? So that's the ChebFun philosophy is all about continuous analogs. Well, there's a piece of that if you like. So let me show you some pictures now of singular values, condition numbers, and so on of random functions. And I guess this discussion, I don't know the literature, but Marchenko and Pasteur is certainly an important paper in this business. So there we have an 80 by 20 random matrix, and we plot its singular values. And I've plotted them on 2 different scales, so it's the same data. It's just one matrix. Often people show histograms, but I'm not doing that. I'm just showing you the singular values of one matrix. So there you have the singular values. There are 20 of them on a linear scale and a log scale. The maximum singular value, and this goes back to Marchenko and Pasteur, is essentially the square root of tau plus 1. I don't know the details, but broadly speaking, that number is 50 years old, but the details of how it gets there and what the distribution looks like, enormous progress has been made on details like that in the years since. Then the minimal singular value is the square root of tau minus 1. What's tau, you ask? It's gamma. I'm sorry, I got confused. It's the aspect ratio of the matrix. So tau is the same as gamma. Yes. By the way, is there a standard letter for the aspect ratio of a random matrix?
I use gamma a lot.
You use gamma, okay. Yeah.
I try to use it all the time.
Yeah. So now what about the continuous analog? Anyone want to predict what it's going to look like? I'm now going to superimpose on that plot the singular values of that object. Oh, what's the singular value? Of course, that's an important question. I haven't told you. All the standard operations of linear algebra have continuous analogs, and it's about low-rank approximation, right? So the first singular value tells you the error in approximation by rank 1, and so on. Right, so it's the same. You do L2, you do low-rank approximation of that function. Yeah.
Would the picture be similar to the one?
To the one?
Oh, I'm just going to do.
Oh, you're guessing what it is? Yes.
He wouldn't have put as many negative powers as he can on the log scale.
So that is very good. You are a good test taker. Yes, you are exactly right. Why is there a log scale there? So Alan, you've got half the answer, and what's the?
I wasn't sure what the scale is.
So Alan is right. The picture's going to look about the same, but this C matrix it is not of finite rank, it's of infinite rank. It's of finite numerical rank, if you like, but then it has in principle an infinite tail of singular values going down to 0. So broadly speaking, my continuous things look like the discrete things we know and love with plunge regions that go down to 0. By the way, in ChebFun, which is all about, ChebFun 2 is thanks to Alex Townsend. Alex has done an incredible variety of things for a man of his youth, even for a man not of his. So one of the early things he did, but even as a graduate student, I mean, there were other things like ultraspherical spectral methods and incredibly fast algorithms for Gauss quadrature. So I've had several impressive students whose names begin with AL. In ChebFun 2, you can produce all of this stuff with short commands like that. So you see, we make a random function with randnfun2, we plot it in zebra mode, and then we take the singular value. So, you know, Alex overloaded the SVD command in MATLAB to give you the singular value decomposition of a Chebfun2, as we call it, a function of two variables. Here's the same picture, but just a bigger matrix. So now it's 200 by 50. So again, you have 50 singular values now, and the continuous analog, again, has a plunge region. Notice there's a discrepancy here, and I'm not making any claims about what approaches what exactly in the limit. Clearly, there's a close connection here, but there may be lower order terms that I don't know about. So, clearly, a random C matrix has infinite rank, but finite numerical rank, which is a fancy way of saying that it's a compact operator. But it's more. When you say this, there's often an implication that there's a plunge region and that most of the stuff is captured in a certain domain, and then you very quickly go down to 0. And by the way, this whole plunge region concept, as far as I can figure out, essentially dates to the incredible trio at Bell Labs in the 50s and 60s. So it was Pollack and Slepian and Henry Landau. And those guys wrote a collection of papers in sampling theory and so on, which it's absolutely the spirit of the kind of numerical analysis we all do today. I haven't shown you periodic random C matrices. So let me say a word here. A periodic random C matrix is defined also by a random series, and then it really is a finite series, so these really do have finite rank. So mathematically, periodic random matrices random C matrices are virtually identical to random matrices. So in that sense, my theme is trivial, but I think the non-periodic case is conceptually the right place to start with randomness. So the plunge region comes from the fact that you're talking about a non-periodic random function. Okay, so now we get on to closer to Alan's great work from a few years ago. What about the square case? So there's a square random matrix, and there are the singular values. And here the big difference is that the square root of tau is equal to 1. So it goes down to 0. So now the edge becomes much more important. And if you want to understand the condition number, you really need to analyze that. So Edelman became famous for his results on that edge. What about the C matrix analog? Well, no surprises. It looks there's the same kind of thing with the plunge region. Of course, you can't say that a C matrix has a finite condition number at all. It has an infinite condition number. What about eigenvalues? So here again, I don't really know the literature, but I believe these are 3 important contributors. So Ginebra wrote a very fruitful paper back in the 60s. Gurko, we talk of Gurko's circular law. Tao and Vu then generalized this greatly. So let's look at that picture. So there's a 50 by 50 random matrix, and the eigenvalues are, broadly speaking, uniformly distributed in the unit disk. What about the C matrix analog? Well, there we are for a case of large lambda. We're not very close to the n that goes to infinity limit yet. Now, of course, there are infinitely many eigenvalues. So which ones am I plotting? And the answer is, ask Alex. I'm plotting whatever Chebfun2 gives me. So that's what I'm plotting. And somehow, of course, Chebfun2 is resolving things down to more or less machine precision, and then giving you eigenvalues associated with that. Here's a finer case with more eigenvalues. And this time it gives us 124 eigenvalues. By the way, some experiments like this were done by my very close colleague, Yuji Nakatsukasa, a few years ago among the Chebfun examples. There's a lot of cool stuff in the Chebfun examples, really, I'm serious. There are about 300 of these, and it's really interesting to prowl around and see what we've got there. There's a 200 by 200 case. And you can see, obviously, broadly speaking, continuous bivariate functions behave like random matrices, but I make no claims about the exact analogy there. There we go up to 500 by 500. Now, I want to mention one of Alan's wonderful papers. So Alan won the Chauvenet Prize for a paper on how many roots of a random polynomial are real. And then they wrote an analogous paper on how many eigenvalues of a real random matrix are real. And in typical fashion, they got exact formulas for these distributions. So that's another amazing paper. So why do I mention that here? Because if you look, you notice, of course, some of the eigenvalues are real. And that's true in the matrix case, and it's true in the real C matrix case. The fraction of real eigenvalues is going to go to 0 as you go to infinity, but there's always a non-zero, for any finite discretization, there's a non-zero fraction of real eigenvalues. And now, it's the biggest one I'm going to show you. You begin to see that something is going on at the origin that's different. And also something's going on outside the unit circle that's different. And I make no claims. I really don't know precisely any of this stuff. Presumably the stuff near the origin is genuine because we have infinitely many eigenvalues mathematically, so they're not going to be uniformly distributed in the disk. Whether the stuff outside the unit circle is genuine or lack of resolution in ChebFun2, I'm not quite sure. I haven't tried to pursue this. I haven't even looked at eigenvectors, which would be an obvious thing to do. Now, what about quasi-matrices? So in the title of this talk, I said eigenvalues and singular or condition numbers of quasi-matrices. I didn't say C-matrices because that's such an unfamiliar word, and I wanted to echo Alan's title. But we should say a word about quasi-matrices, and to remind you, these are continuous in one direction. So we're now talking, for example, about that case. That would be an infinity by 3 quasi-matrix, or infinity gamma by 3 quasi-matrix. And each column is then a smooth random function, and it turns out that the right way to normalize is like that. It doesn't matter what, it's the ratio that matters of the wavelength to the aspect ratio of the rectangle. So I'll just fix tau to be 1, so it's like a, whatever that means, a square quasi-matrix. So let me show you some singular values of n by 3, or infinity by 3 quasi-matrices. So in ChebFun, here's how we do it. We set the domain to be 0 to 1, and I'm going to show you 3 cases. So we have a rand-n fun with a huge wavelength, so very, very smooth. A rand-n fun with wavelength 1, so medium smooth. And a rand-n fun with wavelength 0.01, so not so smooth. And let's first plot these matrices. So you know in MATLAB, if you plot a matrix, it plots the columns. So same in ChebFun with quasi-matrices, you plot it, you get a plot of the functions defining each column. So there are plots of these particular samples. So with the very long wavelength, all the columns look the same. I mean, they're scaled differently, but they're all almost constant. With the medium wavelength, they're all non-constant, but smooth. And then with the short wavelength, of course, they look a little more like noise. And now, can you predict the singular values? So what are the singular values of these infinity by 3 quasi-matrices? Any predictions? What will these look like? Well, I'll tell you. So those functions are all essentially the same. So a rank 1 approximation will capture most of the energy. So the singular values look like something O of 1 plus 2 other numbers, close to 0. How about the middle one? Well, the singular values are 3 numbers O of 1. And the last one. So now we're looking at the singular values of an infinity by 3 object, where the columns of that object wiggle a lot. So those columns will be more or less independent. So the singular values are all more or less 1. And surely it would be, there's no doubt of the theorem here, they really will approach 1 in appropriate senses as the wavelength goes to 0. So that's a continuous analog of the effect that is at the heart of randomized linear algebra algorithms these days. So as many of us know, random vectors tend to be orthogonal as n goes to infinity. When Alan wrote his stuff, this was not in the air particularly. We didn't think of random matrices in terms of randomized algorithms, but this is absolutely what's exciting these days. All across randomized linear algebra and data science, this effect comes in. And I'll just show you a typical illustration. Here we have random, I've just taken pairs of random vectors of different dimensions, and you can see they become approximately orthogonal in this square root fashion as n goes to infinity. And Edelman, by the way, in that original paper, completely nailed this case, the case with 2 columns of a random matrix. You probably don't even remember that you did. Do you remember that you did that? Yuji, who knows everything, did not remember. So if anything in randomized matrices that Yuji doesn't know is impressively obscure. And here's the continuous analog. You take a quasi-matrix with 2 columns, and of course the columns become orthogonal with a square root dependence as the wavelength of the randomized function goes to 0. Here's just the same thing, except with 10 columns instead of 2, showing you that as lambda goes to 0, you're getting more and more orthogonality. And the way I've measured it here is to compare the condition number to 1. So you have a infinity by 10 matrix. As the infinity gets bigger and bigger, you get more and more independence of the columns. The singular values become closer and closer to 1. So the condition number becomes closer and closer to 1 with this square root dependence. And I think that is the whole talk. Thank you very much.
Is there any questions?
This is not so much a question as it is an opportunity to tell you about an area of application for what you're doing here. In particular, the area is called two-dimensional Fourier transform spectroscopy. And it's widely used in chemistry. Richard Ernst at the ETH Zurich got the Nobel Prize in Chemistry in 1990 for his work in this subject. It's not random, but there's a lot of noise in it as well. So they typically work in the frequency domain. So they would be taking matrices or quasi-matrices or C-matrices of Fourier coefficients. And the analyses are typically done there, but they go back and forth between the time and frequency domain. With Fourier transform techniques, the data, of course, is really collected in the time domain. These spectra, the way they process them, are chock filled with artifacts of various kinds from the way they process them. And there's all kinds of heuristics that go into this that really could stand a much closer look from a more mathematical point of view. Yeah. I wrote a paper about 20 years ago, published in Proceedings of the National Academies, which looked at some physically motivated matrix factorizations of these spectra in the frequency domain, by which you could basically pull out the physical data or the underlying physical parameters that they were being measured by these spectroscopic techniques.
So if you could send me some email with some pointers, that would be great.
So.
Thank you very much.
You should definitely have a look at this. It's, yeah, spice up what you're doing with the other.
Any more questions? Okay.
So thanks, Nick. Random functions are quite common in natural systems, but whereas the ones you're describing, the power spectrum is basically a window function, flat window function. Typically in nature, it's falling off like exponentially, like with thermal radiation or power laws with so-called pink noise. And I'm wondering how much that would affect these kinds of results.
So everyone always asks, they say, why are you just doing one case rather than studying Gaussian processes in general? And I guess the answer is that mostly I'm interested in the limit as n goes to infinity, where many properties, though not all, of course, will not depend so much on what correlation function you choose. But I realize there's a whole world out there of Gaussian processes in 1D, and then in higher dimensions, Gaussian random fields, and they always want to know how pink is your noise.
We will take one more question.
So I'm wondering, you chose to look at singular values as scalars, numbers. Did you ever think about instead, does it mean anything to think about singular values being functions themselves?
Yeah, Jacob White here, by the way. I don't know. I only connect singular values with finite rank approximations. But everything has a continuous analog. Maybe that does too.
Nick, do you want to, Nick, do you want to repeat the
Acceleration method.
The question is, in some sense, what about continuous interpolates of singular values rather than viewing them as so discrete, right?
Well, not necessarily singular values to a number, it could be a function.
Of parameters?
Well, I don't know. Maybe it
Yes.
doesn't-
It could be a function, but I don't have nothing to say about that. I haven't
The
thought
low
about
rank approximation is an integral, right? Instead of the sum of rank one things, you have an integral times the singular value, right? So,
it. No, it's still a sum.
but that would be.
Oh, that's what you're saying.
That would be a continuous analog, right?
Maybe, and I haven't thought about that.
So let's think, Nick, again.